this lecture we will try to look at some applications of linear algebra, and there are numerous applications of linear algebra, as I have said, in diverse fields, including the extreme problem of medical imaging in CT scanner, MRI and all that. That is probably one of the ultimate applications of linear algebra. But you also have more janta applications where a lot of common people also use, particularly in the audio video space. We will take a look at that. For that we need to build some background, and we will do that in this session. Okay. Recall the following. Recall a real matrix is orthogonal, a real matrix U is orthogonal if U transpose U equal to U transpose is identity matrix. Okay. Similarly, a real matrix U, small correction, a complex matrix U is Hermitian if UHU equal to UH equal to I. Okay. So, this is orthogonality in the real vector space. This is the equivalent of orthogonality in the complex vector space, that is all. Okay. So, the critical idea for both is orthogonality. What does this orthogonality do? You also recall another important result. What is that result? Suppose you have a function f of t and you have an orthonormal basis of vectors 1 sin theta, sin 2 theta, etc., cos theta, cos 2 theta, etc. Now, if you project f of t onto the space spanned by this set, the coefficients you get for each term 1 sin theta, sin 2 theta, cos theta, cos 2 theta, etc. These are basically, this is your equivalent A naught by 2, this is A1, A2, this is B1, B2, meaning your f of t is represented as A naught by 2 plus A1 sin theta plus A2 sin 2 theta, etc., plus B1 cos theta plus B2 cos 2 theta, etc., etc. So, these A naught, A1, A2, etc., B1, B2, this indeed is what is called your Fourier series coefficients for the function f of t. What are these basis vectors or basis functions? 1 sin theta, sin 2 theta, etc., etc., including cos theta and cos 2 theta. You know very well that they are orthonormal. So, you are basically expanding the function, expanding function f of t, which is also called representation in the terms of Fourier basis. When you choose a Fourier basis, which is the set 1, this set, this Fourier basis, the coefficients you get are the Fourier series coefficients. Okay. Now, what is interesting is, can I look at only this basis? Say 1 cos theta, cos 2 theta, etc., etc. I am looking at only cosine terms. In fact, this set, which set? This set 1 cos theta, cos 2 theta, etc., etc., is also a orthonormal basis. This is used for what is called cosine series expansion. So, not only the original set is orthonormal, a subset of the taking only cosine terms is also orthonormal. You could have chosen this set 1 sin theta, sin 2 theta, etc., also. This also is orthonormal, but for all practical applications, which we will look at shortly, we prefer this set 1 cos theta, cos 2 theta. So, we prefer the cosine over sine. Question is why? Why do we choose cosine functions over sine functions? It is not necessary that you always choose cosine, but a majority of applications choose this set cosine n theta set, n equal to 0 to infinity. Of course, we will make it finite eventually for convenience. There are many explanations. One, let us look at audio. In the audio applications, typically you have a waveform and that goes into the ear and the sound is perceived through the brain. Okay. Now, question is, what does the ear hear? The ear is a sensor. So, when audio waveforms are put, they induce pressure waves in the air column that comes and hits the ear. So, what ear gets is pressure waves modulated according to the audio signal, pressure waves impinging on eardrum. Then of course, there is auditory, neuroauditory process and all that. We will not worry about that right now. So, what are these pressure waves? These are basically energy functions, not amplitude alone. even though you have an amplitude here, let us say some A magnitude, what the ear perceives is proportional to square of the amplitude. That is something to understand, because energy is an even function. Take your simple Ohm's law. It is also true of all your mechanics, physics laws. When you look at energy, energy basically is I squared R or V squared by R, which means proportional to I squared or proportional to V squared. So, energy functions are even because it is of the type y equal to x squared. Even function. What about cos function? Cos theta. How does cos theta look like? Cos of minus theta is cos theta. So, f of x is equivalent to f of minus x, even function. Whereas, look at sin theta. Sine of minus theta is minus sin theta. So, f of minus x is minus f of x, odd function. So, significant audio and video, therefore, entire multimedia is built on using cosine function to code, and these are orthonormal. One fact: whenever you use an orthogonal system, the representation of using that is in some sense minimal or optimal, or you want to call it best. Meaning, whenever you have data or function, if you use an orthogonal, or if it is orthogonal, even better would be orthonormal, which is not a difficulty, you get a compact representation. So, this is the trick involved in what is called data compression. Lot of audio and video data is coded using orthonormal basis, and even though there are better ones, the most convenient is cosine set, cosine series. Of course, we will make it finite. So, instead of cos n theta ranging from n equal to 0 to infinity, we will have cos n theta ranging from 0 to let us say n minus 1. So, n length or n terms n terms. Now comes how do we use this? How do we use this? For that we need to go back and understand what this idea of frequency, domain, representation. We know what we know so far, that given f of t, I can put it as a naught by 2 plus sigma a n sin n omega t plus sigma cos n b n cos n omega t, n equal to 0 to n equal to 1 to infinity, n equal to 1 to infinity. This is f of t. A more interesting application when this f of t is aperiodic, which is more common than periodic. We have a cousin of Fourier series, called the Fourier transform. This Fourier transform is also a linear transform, like what you have done linear transform. You did that some t mapping from x to y space, you have done that. So, t of alpha x 1 plus beta x 2 maps to t alpha y 1 plus beta y 2 for all alpha beta. So, you have a definition of linear transform which maps vector space x to y. Linear transform, this Fourier transform by definition is integral 0 to infinity f of t e to the power minus j omega t dt, that gives you a definition of f of omega. Is also a linear transform. It has all the properties scaling and superposition. Whatever you did to a matrix transformation or generic t mapping from x to y is also valid here. So, it is a linear transformation. You would have studied many of the properties. What is more interesting is the following. This is good, best represented by an example. So, let me take f of t to be e to the power minus a t. So, in time domain it looks like this. T, this is f of t. What is f of omega? Is integral f of t e to the power minus j omega t dt, that will give me e to the power minus a t, this is 0 to infinity, e to the power minus j omega t dt. If I work it out, I am going to get 1 over a plus j omega. This will be f of omega. F of omega is complex. Therefore, it will have a real part plus imaginary part. So, what do you do when you have a complex representation? Complex representation is normalized. Then if you do that, multiply and divide by a minus j omega, you are going to get a minus j omega divided by a squared plus omega squared. So, you have a real part a 1 over a squared plus omega squared minus j omega over a squared plus omega squared. Now, I can, this is again real and imaginary part, I can find the magnitude. If I find the magnitude, I am going to get the following: magnitude of the Fourier transform versus representation omega. This will be 1 over square root of a squared plus omega squared, that will be the magnitude. I will do magnitude squared. Going to get like this. This will be an even function. Magnitude squared of the Fourier transform is energy function. So, when you are playing music or audio, what the ear is hearing is square of the magnitude of the Fourier transform of this function. So, at particular frequency omega 1, omega 2, omega 3, which corresponds to f1, f2, f3, you hear these values, they are continuous, no doubt. Because you are using a even function, you end up with the concept of minus omega, which does not exist anywhere. So, because you are now facing the issue of trying to represent the magnitude squared of a function which is equivalent to energy function, you live with it even though your focus is only on the right hand side part. So, ear hears, what does it hear? It hears magnitude of the square of the Fourier transform, magnitude squared of all frequencies between 20 hertz and 20 kilohertz only. This is that. So, between 20 hertz and let us say 20 kilohertz, this is all the ear hears. This is an even function. Cosine is an even function. All cosine functions are even for any order, cos n theta. So, I have an even function, I want to capture a even function with terms which are even. Therefore, the match is very good. If I try capturing this with an odd function, right, odd function, I am in trouble. Matching is not good here, whereas all even functions, that is the reason why the cosine series gives very good match, which means minimum terms, minimum non-zero terms. That is the reason. Of course, we eventually will use it in the discrete form. So, the discrete cosine transform vis-a-vis the discrete sine transform, which are both cousins of the discrete Fourier transform, this DCT dominates. DFT is Hermitian, this is unitary, this is also Hermitian. Of course, if you drop out all the complex terms, you still look like a unitary transform, but the real part of DFT is a cosine function associated with DCT, the imaginary part is associated with DST. So, we will look at this both for audio and video. Okay. Now, how do we go about discrete version? How do we go about the discrete version? Basically, I have this, let us say f of t, whatever the function. I got an f of omega magnitude square, let us say like this. There are many steps. The first step is to convert f of t to f of n, which is I discretize so this function f of t became a sequence f of n. Further, I can make it finite. So, f of t, which was from 0 to infinity, became a sequence f of n from 0 to let us say n minus 1 terms. So, 0, 1, 2, 3, 4, n minus 1 terms. So, I make it n length. This is on this side. On this side, I want this. I want to discretize this in frequency too. How do I discretize in frequency? For that, you recall the following. Suppose I have sine omega naught t, which is sine 2 pi f naught t. This is t versus f of t. How does it look in the omega space, which is 2 pi f space? How does it look? It has only one frequency component f naught. So, here at some value f naught, there is only one component, or this is how magnitude of f of omega squared looks like. So, discrete in time is equivalent to periodic in time is equal to discrete in frequency. What we do not do is the following. We had discrete sequence f of n. We suppose repeat this f of n. All the way to infinity. I am now going to get discrete in frequency, in principle we do not do this, but if it is done you end up with this. So, I got discrete in time, finite, discrete in frequency, but not at finite. Okay. So, next effort is to make it finite in frequency. This we sample, truncate, periodic extension, etc. Various versions are there. So, finally, I am going to have this. I have discrete finite f of n is equivalent to discrete finite f of omega magnitude squared. This will be 0 to n minus 1 since we look at 2. So, each width is 2 pi, which is 180 degrees, 2 pi by n. This is the resolution of frequencies. Now, we are in business. We have finite discrete sequence in time, finite discrete sequence in frequency. We will use this to do our audio video applications, which will also give you a clear idea of why orthonormal basis functions, transforms, unitary transforms, Hermitian transforms are so commonly employed in all the applications of signal processing, image processing, communication, vibration problems, control problems, etc., etc. Okay. So, this is in some sense the summary of this session, where we looked at Fourier series, we looked at Fourier transform, we looked at functions and their discrete version and their finite version. We also looked at the Fourier transform, we looked at the magnitude squared of the Fourier transform plot. We realized that this is even, and even function must be best represented by orthonormal functions, basis functions, which are even, which is the cosine series. In the next lecture, we will look at audio and video applications using orthonormal basis. And this is just the beginning. The whole family of orthonormal basis, unitary transforms, Hermitians occupy the whole range, and there is some very elegant connection between these transforms and eigenvalue eigenvectors. There is one transform called KLT, Carnot-Levy transform, which is made up of eigenvalues and eigenvectors. Using eigenvectors very similar to what you did for diagonalizing, but these eigenvectors are also used for data compression, coding. They are very elegant, they are better than the cosine and the DFT. The only problem we do not use them is calculating eigenvalue eigenvectors all the time is very challenging, time consuming, resource this thing, whereas cosine or the closest approximation to KLT, but very easy to represent code and use. So, 90% of the applications is built on DCT and DFT, very few are built on KLT unless it demands such high orders of compression and so on. We will look at it in the next session. Thank you.